for part 1 circuit. First of all, we take out all the components first. First we take DC current, and then the resistor, and finally ground. Okay, and then we connect them with the lines. Connect. Okay, so this is the complete circuit for part 1, and then based on figure 1, it is set to 10 milliamperes. So 10 milliamperes, and the resistor is set to 100 amperes. And then finally we place the probe, which is to measure voltage for this circuit, and then click run. So the voltage for this circuit is 1 volt. And one more thing, to get the value of 100 ohms, which is the resistance value, according to Ohm's law, to find the resistance, you have to divide voltage with the current. So 1 volt divided by 0.01 ampere. You have to convert milliampere to ampere first to divide with the volts. So we will get 100 ohms as the resistance value. Okay, this table is for part 1. So this is the value that I have recorded, which is 100 ampere from multisim, and from calculation, which is volt divided by the ampere, and we still get 100 amperes. Okay, so this is the circuit for figure 2. We have a DC voltage, a resistor, and a ground. So for DC voltage, according to the lab sheet, it is 10 volt, and for the resistor is 100 ohms. So if we place the current, to measure the current, we put it here, and then we press play. We will get 100 milliamperes for 10 volts. So if I change it to 2 volts, let's say 2 volts, we will get a different result. So we click play, we will get 20 milliamperes. Okay, I'll try one more. We'll put it at, let's say, 8 volts. So when we put it at 8 volts, we'll change the current to 80 milliamperes. So these are the values that I have recorded for figure 2, from 0 volts to 10 volts. So it goes from 0, 20, 40, 60, 80, and 100. And also the values for multisim and the calculation are the same, so there's no difference between them. So this graph is for table 2. So volts in y-axis and current in x-axis. So to find the resistance of this graph, first we take the maximum value of volts, which is 10, and minus the minimum value, which is 0, and then divide by the maximum value of current, which is 100, and minus the minimum value, which is 0. So I put 0.1 here because I converted 100 milliamperes to amperes, which is 0.1. So after the division, we get 100 ohms. for the resistance.
Hello, my name is Hanif Helmi and I'm in group with Hanif Jamaluddin. Today I will explain about part 2. So basically in part 2 they give me the circuit and then I have to do it in the multisim. Okay, this is the circuit. Okay, the first question is to measure the voltage. Okay, after run the simulation, this is the voltage what I got. Okay, this is VAB, VBC, VAD, VDC, VBD and VAC. They also tell us to calculate the voltage is to calculate the voltage we use the Ohm's law, which is V is equal to IR. And then this is the result that I get. Is it the same as the measurement at the multisim? Okay, and then we have to find the sum of current at naught. This is for the current, so I run the simulation. This is what I get. Okay, this is what I get, which is this IMB, ICB, IAD, ICD, and IFA. We also use the Ohm's law to calculate the sum of current at naught. Okay, and then we have to find the voltage around the loop. Okay, to find the voltage around the loop, we use the Kirchhoff current law. The Kirchhoff current law second law state if the knot starting knot find the same knot, the voltage will be zero. The voltage will be zero in the closed loop. That is the Kirchhoff current law state. Kirchhoff second current law state. So the multisim also zero. Calculated also zero. So basically the answer is zero because it is the closed loop. Okay, the last one is current at the knot. Okay, after I set up the something like the emitter, I think, then we get the value measurement of the current, not A, not B, not C, not D, like that. Okay, and then we copy the answer at the table, and then I'm done. That's all from me. Thank you.